Okay. All right. So let's continue our discussion of real numbers. Let's see. Okay. We will see the concept of Cauchy sequence. This notion of Cauchy sequence is very similar to convergence, but actually it is, philosophically very different, and we will see this in detail. A sequence an of real numbers is called Cauchy if following happens: if for any epsilon positive given, there is some index again n0, n0, so that m and n larger than n0 implies, so this condition implies that the distance between an and am is less than epsilon. Okay, so here we are not talking about terms of a sequence being close to a real number. Here we are talking about a sequence whose terms are close to each other. How close? As much as I want. So you give me an epsilon. This could be any real number which is positive. It could be very small as you want. I guarantee that there is some n0, so that after after this term, let's say this is 500. So the terms of the sequence after 500, so A500, A501, A502, and so on, all these terms are close to each other at most with a distance at most epsilon. Okay, if you give me a smaller epsilon, then I may have to choose this n0 big. Okay, maybe I'll choose n0 1 million, so that all the terms with index larger than or equal to 1 million will be close to each other, with a distance at most that epsilon, whatever that is. Okay. And the first observation is the following: if a sequence is Cauchy, okay, I said it wrong. If you have a convergent sequence, then it must be Cauchy. Why is that? You see, convergent means the terms of the sequence are close to a real number, a fixed real number, let's say L. But if they are very close to L, then they must be close to each other, because they are close, all of them are close to a single real number. Then all these numbers should be close to each other. That's the observation. Any questions so far about this definition? Okay, if you don't have a question, then I'll start with our first observation. Proposition. The content is just what I said a minute ago. A convergent sequence is Cauchy. So any convergent sequence is Cauchy. And the proof is again simple. What I said, First, let me draw you a picture. Convergent means there is some limit point L, and the terms of the sequence are very close to this L. But if they are very close to this number, then they must be close to each other also, right? That's the idea. How we will write it? Well, I have to just use the definitions. Okay, so for convergence, this is how it is written. Given epsilon positive, okay. Well, I have to find an n0 so that if m and n are larger than n0, then the distance between these two terms should be less than epsilon. And you see, I can always do this. The distance between these two is less than the distance between right, using triangle inequality. I add and subtract L, and then I group them like this. So this is less than an minus L, and then this is less than L minus am. So if I can make this less than epsilon over 2 and this one less than epsilon over 2, then the sum will be less than epsilon. So that's the idea, okay? So if the terms of the sequence is very close to L, then they are close to each other. Okay, so since epsilon is positive, epsilon over 2 is positive, then epsilon over 2 is positive, and since we assume that since an is convergent to some L, there is some index n0 so that n greater than n0 implies an minus L is less than epsilon over 2, right? That's the definition of being convergent, right? For any epsilon, well, epsilon over 2 is also a positive number, so it's just a positive number. Therefore, if the limit is equal to L, then I can find an n0 so that n larger than n0 implies this. But then, hence, if n is larger than n0, then we have what? We have this. An minus, sorry, I should write if m and n larger than n0, because that's the definition of being Cauchy. The distance between an and am is what? I wrote this like this. Right? I added and subtracted L. Then I use, as usual, triangle inequality. Okay. And then I know that if an index is larger than n0, then the distance of the corresponding term to L is less than epsilon over 2. Here both m and n are larger than n0, therefore both of these distances is less than epsilon over 2, and this is just an epsilon. This is the epsilon. So we are done. Why is that? You see, here is the argument for being Cauchy. You give me an epsilon, I choose some n0. If m and n are larger than n0, then the distance between an and am is less than epsilon. So this finishes the proof, okay? Thus, an is a Cauchy sequence. So any Cauchy sequence, any convergent sequence is Cauchy, okay? All right. Okay. And when it comes to real numbers, we will see that actually any Cauchy sequence is convergent, but it will take some time to prove that. First, we need a fact, some facts about Cauchy sequences. Do you have any questions so far? Okay. Another proposition is this. You see, if you have a Cauchy sequence, this means what? The terms of the sequence are getting closer and closer to each other. In particular, let's say you choose your epsilon to be 1. This means what? There is some index, so that after that index, all the terms of the sequence are at most 1 unit apart from each other. Let's say that index is 10 million. So if the index is larger than 10 million, if you choose two indices larger than 10 million, then the distance between them is less than 1 unit. In particular, all the terms of the sequence is close to the 10th million term with distance at most 1 unit. The terms with index larger than 10 million. This means the tail of the sequence is close to a fixed real number. The first 10 million terms can be far away from this term, but there are just finite many such terms. This means that all the terms of the sequence are close to a fixed term with a fixed distance, and this means that the sequence is actually bounded, okay? The terms cannot go to plus or minus infinity. So that's the second observation. So observation is this. Any Cauchy sequence is bounded. Okay? And the proof, I just actually try to describe you the proof verbally. Now I need to write it down in details. Okay. Since it is Cauchy, it satisfies the definition for any epsilon I choose. So we let epsilon to be 1. Let epsilon to be 1, which is a positive number. Then, so since an is Cauchy, let's say my sequence is an, okay? Cauchy sequence is an. Since an is Cauchy, maybe any Cauchy sequence, let me write it this way. Any Cauchy sequence an is bounded. is Cauchy. There is some index n0 so that m and n larger than n0 implies the distance between a and am is less than epsilon, which is 1 in this case. In particular, we have this an minus an0 is less than 1 for all n greater than n0. I just choose my m to be n0. I can do that. So this becomes an minus an0 is less than 1 for all terms with index less than greater than n0. Okay. Well, this means, I have something like this. an0 is somewhere here. I go 1 unit to the left and 1 unit to the right. So this is an0 plus 1, and this is an0 minus 1. And all the terms of this sequence are inside this interval. Here is, let's say, an0 plus 1. Here is an0 plus 2, and so on. But this is true if n is larger than n0. So the terms with index less than n0, they do not, have to lie inside this interval. They might be outside. But there are only finitely many of them. And I can, let's say a1 is here, a2 is here, a3 can be here, and a5 is here. But there are just finitely many such terms, and I can choose the distance from n0 to the to those elements and take its maximum of finitely many numbers. That will be a finite number, and then I'll choose my radius to be that maximum. So this is how I will proceed. That's the idea. Let me now write that down. Okay. Let m to be this: maximum of 1 and distances between an and an0 okay, let me write it this way: distance between an and n0 for n less than n0. Okay, I just look at all the distances from the terms of the sequence with index less than n0 to an, and choose the maximum. But to be on the safe side, let me add 1 to this real number. Whatever that maximum is, I add 1 to that. But then, now, oops. Now, the distance between an and an0, what is this distance? Well, whatever that thing is, this number is less than m. Why is that? If n is less than n0, so this is either Okay, so this is less than m if n less than or equal to n0 minus 1 and an minus an0 is less than 1, but 1 is less than m because m is just 1 plus something. So this is less than m if n is greater than n0, right? So in both cases, if n is larger than n0 and if n is less than n0 minus 1, in both cases, this difference is less than m. Hence, an minus an0 is less than m for all n. Okay? But this means what? This means the following. An minus an0 is less than m and greater than minus m, right? For all n. And this means an is less than an0 plus m and minus m plus an0. And this means, right, the absolute value of an is less than maximum of these numbers, whatever that is. So let's say k for all n where what is k, where k is this number. Just choose k to be the maximum of the absolute values of these numbers. Maximum of minus m, sorry, absolute value of this and absolute value of this. For example, this number could be minus let's say 100, and this could be just 0. So in that case, I have to choose my k to be 100, right? Or this could be, let's say, 3, and this could be 5. Then I choose my k to be 5, right? So we have to be careful there. So what we see is then all the terms of the sequence is less than k, right? For where k is this real number. Hence, an is bounded. But you see, the idea is very simple, right? The terms of this sequence are very close to each other, right? So I just pick one of those terms, and then I see that all the terms, the other terms, are close to this number if the index is large enough. What about the indices which are not large enough? Well, for those indices, I just look at the distance between this fixed term and those finitely many terms. I measure distances, I take the maximum distance and add 1 to that and so on, and then I finally come up with a real number so that it satisfies this condition. Okay, we just play some easy games. Any questions so far? Oh, okay. The uh, uh, Well, actually it depends. Maybe I don't need actually that number, but let me see. uh, if I, you know, okay, in the, yeah, actually you are right, I don't need that one. I've at some moment thought that I need strict inequality for, you know, in the definition of being bounded, but I think I defined uh, boundedness using uh, not strict inequality, right? Bounded means the terms of the sequence is less than or equal to some term. Yeah, you are right. Actually, I don't need this one. Uh, if I erase it, it won't cause any problem. Yes, you are right. Sometimes, you know, if you need strict inequality, then taking maximum won't be enough, because then that number will be greater than or equal to, you know, whatever that new thing you defined. But if you need a strict inequality, that's not what you want. That's why you may have to add something to that so that it will be strictly bigger than, you know, your expression. But in this case, you are right, I don't need. Uh, is it okay now? Any other questions? No problem. Okay. Any other questions so far? Okay. Okay. Maybe I do some more examples. Uh, a constant sequence, right? A constant sequence is always convergent, right? Convergent. And thus Cauchy. Why is that? Well, so I have a sequence an, and this sequence is like this: some fixed number, c, 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 right? Constant. All the terms are equal to each other. I claim that this is convergent. Why is that? And actually we claim that limit of an is equal to c, right? The limit value is c. Why is that? Well, we have to just write the definition. Given epsilon positive, I have to choose an index so that the term with index larger than that index minus c will be less than epsilon. But here you see all the terms are equal to each other, so an minus l, which will be just c minus c, and this is 0 and it is less than epsilon. So I can choose my n0 anything I want. Given epsilon positive, just choose n0 to be 1, for example. Then if n greater than n0, which is 1, then the difference between an and c, the claimed limit number, will be what? Well, an is just c, c minus c is just 0, and this is of course less than epsilon, and this finishes the proof. Okay, so here is the argument. If I underline the important parts, given epsilon positive, I choose some n0. If n is larger than n0, then this distance is less than epsilon. That's it. Okay. All right. What else? Okay. I said examples, but I think I'll do one example at the moment. Let's say example. This sequence is convergent and also, of course, Cauchy. Now, let's talk about increasing and decreasing sequences. So this is another definition. Okay. A sequence of real numbers an is called increasing respectively decreasing if what happens if an is less than an plus 1 and respectively an is greater than n plus 1 for all n. Okay, so if the terms of the sequence are uh, uh, getting bigger and bigger, then we call it increasing. If the terms of the sequence are getting smaller and smaller, then we call it decreasing. So example, this sequence, let's say 1 over n. What is this? 1, 1 over 2, 1 over 3, 1 over 4. Right? This is decreasing. Decreasing. Another sequence, let's say bn. So what kind of sequence is this? If you put 1, you get 1 over 2. If you put 2, you get 2 over 3. If you put 3, you get 3 over 4. If you put 4, you get 4 over 5, and so on. And this seems like increasing, right? Increasing. One has to prove this, right? This is my guess that this is increasing, but let me write this as an exercise. You can prove this using maybe induction, or maybe you can prove it directly. Show that Bn is increasing, is an increasing sequence. Okay. What about this? Let's say Cn let's say this is a constant sequence. Let's say C, C, C. Okay. Constant sequence. Is it increasing? Yes, right? All the terms are, each term is greater than or equal to the previous one, and it is also decreasing. So this is both increasing and decreasing. Another example, let's say dn to be minus 1 to the power n. So this is like minus 1, 1, minus 1, 1, minus 1, 1. So sometimes, next term is bigger, sometimes it is smaller, right? It goes like this. So this sequence is neither increasing nor decreasing. Okay. What else? Oh, I have also the following definition. It is slightly more general than being increasing and decreasing. A sequence, let's say an, is called eventually increasing or uh, eventually decreasing if there is some index and 0, so that uh, the tail of the sequence, so that this sequence an0, an0 plus 1, an0 plus 2, right? This sequence is increasing or respectively decreasing. So I don't care about the first, let's say, 500 terms. If the sequence becomes increasing after some index and on, then I call it eventually increasing. And if it becomes decreasing after some index and on, then I call it eventually decreasing. Okay. All right. I guess we come to a point a friend of yours mentioned in the last hour, namely, okay, or maybe before that, yeah, I have another, okay. Yeah, we need some more, maybe little facts. One of them is the following lemma or proposition. All right. Okay, my maybe next time we will prove the following. And we have seen that convergent sequences are Cauchy and Cauchy sequences are bounded. And we will prove the following fact. If you have a bounded sequence and if it is eventually increasing or decreasing, then it will be convergent. But to achieve that result, we need some intermediate steps. One of them is this one, uniqueness of limit points. Uh, okay, a sequence an may converge to at most one limit value. So we cannot have a sequence which converges to two different real numbers. You know, one limit is, let's say, L1 and the other limit is L2, and they are different. Such thing is not possible. And the proof is very similar to what we actually seen before. If you have two different limit values, okay, then we would have a contradiction. Why is that? Well, you see, if L1 is a limit value for a sequence, then all the terms of the sequence must be very close to L1 after some index, right? So they should be here. But since this is a limit point also, after some index, all the terms of the sequence must be here. And if I choose this interval so that they have no common point, then those indices, you know, big indices, terms with big indices must be also, you know, in this interval and in this interval, but that's not possible because these two intervals has no common point. So that's the proof. That will be the proof. Uh, I have only 5 minutes, so I will not go into the proof. I'll stop here. Next time we will. I will remind you this proposition and prove it, and then we will continue our discussion on sequences. As I said, our ultimate, evet, soru, any questions? Söyle. Uh, okay, I'll do that. Okay. Bir şey değil. Okay. Let's stop here for today.